E2 reactions are also stereospecific, which means the stereochemistry of the starting material will tell us the stereochemistry of the product. So, in this case, if we're going to draw our mechanism, the hydroxide will attack the hydrogen, form a new pi bond, and kick off the chlorine. So, let's have our new alkene drawn here. There are technically two products we can have. We can have one where the ethyl group is on the top, and we have this cis isomer, or we can have the isomer where we have a trans isomer. In this case, only one of them is correct though, so we have to figure out which one that is. So let's consider the Newman projection of this molecule. That'll help us visualize it. So let's look down this axis here. On the front carbon, we have a hydrogen on the top. We're going to have a methyl group to the left and an ethyl group to our right. On the back carbon, the chlorine is on the bottom. We have the methyl group on the right and the ethyl group on the left. For us to be able to form a new pi bond, we're eliminating the hydrogen and the chlorine, and remember, we're going to make a system where we have an overlap of two p orbitals, something like this, which means the hydrogen and the chlorine have to be on the same plane, and they have to be opposite from each other. This is called anti-periplanar. So for an elimination reaction to proceed, we need an anti-periplanar conformation where the proton that's being abstracted and the chlorine, or the leaving group, are on opposite faces. So if we're having this reaction proceed, what happens to our substituents? Well, the ethyl group on the left will be over here. Remember, that's the one in the back. The methyl group on the front will be here. The ethyl group on the front will be on the right side, and the methyl group on the back will be on the right side. So what does the stereochemistry of our product look like? So again, the front methyl group is on the opposite side as the back methyl group. So in which product is that true? It's true in this product. So the front methyl group, this one here, is on the opposite side as the back methyl group. If we had the opposite stereochemistry, we would get the opposite product. We'd actually get the cis product instead. So let's take a look at this more complicated example. The first thing we need to recognize is that we have two sites of beta hydrogens. We have one back here, and we have another one here. We can eliminate either one of these and it'll give us a different substitution of a product. For example, if we eliminate this hydrogen, we will end up forming an alkene right here, which will be only a mono-substituted alkene. So we know that that's not correct. If we eliminate this hydrogen, we will form a new double bond here, which will give us a 1, 2, 3 tri-substituted alkene. So we know that that will be the favored product just based on regioselectivity. Now that we've determined the location of the double bond formation, we have to determine whether or not the E or Z product will be formed. So let's draw each of those. In one example, we've got our new double bond formed. We've got the ethyl group down here. We've got this large group here, that's a T-butyl group. I'll just write T-butyl for short. And we have the methyl group down here. That's one of the isomers. In this case, this is the highest priority, so this will be the opposite, or E isomer. Or we can have it formed where that methyl group, instead of being pointed down, is pointing up. In this case, this is the Z isomer. So which one of these is actually formed? Let's go ahead and draw a Newman projection and then figure out how we can make this anti-periplanar. So if we look at that front carbon, we have a T-butyl group on the top, we have an ethyl group on the right going down, and we have a hydrogen on the left. If we look at our back carbon, we've got the methyl group going down, we're going to have our chlorine on the right, and we're going to have a hydrogen on the left. So again, if we're going to have an elimination reaction, we're going to have to do an anti-periplanar attack where the leaving group is on the opposite face as the hydrogen that's being abstracted. So let's go ahead and basically cross these two out. They're already opposite, we don't have to rotate the bond at all, so let's redraw it with those eliminated. So we've got our front with the T-butyl, which will be opposite of the ethyl. We've got a new pi bond forming here. In the case of the back carbon, notice the hydrogen here is on the same face as the T-butyl. So we have our hydrogen here. And the methyl group is on the same face as the ethyl. So our product will have the hydrogen and the T-butyl on the same face. So if we're looking at the examples here, that's going to be our E isomer. The hydrogen and the T-butyl are on the same face of our alkene.